to the future. We are now in the last part, on the second part of the presentation, where we should deal with future technologies, eliminate the complete carbon dioxide emission of the mobility in Europe, just to reduce the increase of the carbon dioxide being produced in China by this process. So that's why we are making a lot of pressure to the official guys in China to combine coal to liquid technology with carbon sequestration, because this is the only technology then to keep it at the same level as today's fuels. And then we can add the biomass, which is reducing carbon dioxide. We also see a pretty good possibility for the connection in between two different worlds, the liquid hydrocarbon world and the hydrogen world. Because if you add renewable hydrogen to such a synthesis process, you can double the output on hydrocarbons. And this is due to the fact that the carbon to hydrogen ratio in the biomass is just on the wrong side. We normally double the hydrogen in relation to carbon, and we have double carbon in relation to hydrogen currently. So in adding hydrogen, each carbon molecule could be fitted with some hydrogen together, so we get the maximum output. And this leads to the fact that you can double the output on hydrocarbons if we add the same amount of hydrogen as already is in the biomass. Now this is a proper possibility to add it. On the other way around, as a synthetic gas is containing a lot of hydrogen, and it could be increased by a water-gas shift reaction, so we get roughly only hydrogen as an output. This could be an excellent possibility for the reduction of renewable hydrogen. And it is from all the production possibilities is the cheapest one. The cheapest possibility to make a renewable hydrogen is via gasification out of biomass. So again, there is a proper link of a synthetic fuels production with a future technology, with a far-away future technology which might come into the market, the hydrogen and fuel cell technology. If now a producer is building up such a facility, it's absolutely sure that it can run within the next 100 years. Because no matter what would come out, he could produce hydrogen, he could use hydrogen, he could produce liquid hydrocarbons, and he could produce base components for biochemistry. Because we can, via this synthetic process, we can nearly synthesize each kind of plastics material we want to have. So it's a base even for a biomass-based chemistry. This is the idea behind the CO2 neutrality, just a simplified picture of it. During growing of the biomass, carbon dioxide is put out of the air. That's a necessary component for the growth of the biomass itself, of the trees in example. This is transferred in this gasification process into a liquid hydrocarbon. The hydrocarbons are burned in the combustion engine, and exactly the same amount of carbon dioxide is coming out of the tailpipe, which has been previously taken out by the biomass out of the air. So in the ideal case, this circuit is completely closed. And this is the same as the nature is handling carbon dioxide. It's driven in a circuit. No circuit in the nature runs without any energy input. And the energy input here is the sun. And that's why we call such a fuel sun fuel. And that's on all our pretty logos here. You can get later on. So in an ideal case, you would have 100% carbon dioxide neutrality, and this would solve all our carbon dioxide or greenhouse gas problems. Because it's not necessary to be carbon dioxide free. God bless that it's not free, otherwise we would be frozen here on the Earth. So we need some carbon dioxide in the air, but it should increase continuously year by year, as it's currently the case out of the use of fossil primary energies. So, yes, please. The complete energy used for the process is coming out of the biomass. That's the secret behind high carbon dioxide efficiency. If you are using fossil energy to drive the process, you're adding black carbon dioxide, which is bringing down or lowering your carbon dioxide efficiency. In the BTL process, we're using some of the biomass for the firing, for the heating and the cooking of the process, so that we have an energy efficiency of about 50%. So 50% of the energy in the biomass is finally in the fuel. The rest has been used for the driving of the process, but it's not necessary to put any fossil energy in to drive the process. That's why we have an excellent high carbon dioxide balance. It's a question of the goal you have. If you would maximize the output, you could add fossil energy. If you would maximize the carbon dioxide reduction, you shouldn't do this. So you can use it, the biomass as an input energy for the process. It's very simple. During the gasification process, you just have to put a little bit oxygen in. And that is all, then immediately getting a standard combustion. And this is delivering the temperature and the heating and the hot water we need for the process. So it's just by adding some slight oxygen to the process. So that's our goal, to close the circuit, and we want to get as near as possible, and we want to increase the quantity as far as possible.